Okay, today we're going to be discussing how to determine the spontaneity of a reaction. Now, what is a spontaneous reaction? A spontaneous reaction is one that occurs on its own without outside intervention. An example of a spontaneous reaction would be a combustion reaction. So, normally in a combustion reaction, you don't need an outside force pushing the reaction forward. All you need is a spark, and the combustion will occur. An example of a non-spontaneous reaction, however, would be this one, also known as the Haber process, which forms ammonia. Now, this reaction won't go forward by itself. You need to have a lot of pressure and temperature on this end to make the reaction go forward to create your ammonia, which makes this a non-spontaneous reaction. To determine a reaction's spontaneity, you need to know your Gibbs free energy, also denoted as delta G. If your Gibbs free energy is positive, that means that your reaction is not spontaneous. However, if your delta G is negative, that means your reaction is spontaneous. Okay, now we're going to discuss each part of this Gibbs free energy equation so that we can calculate the spontaneity of a reaction. Here we have T, which just means that whatever temperature this reaction is occurring at, that's what you plug in here for temperature. Now we have delta H. Delta H is known as the change of enthalpy of a reaction. Enthalpy, to be put in layman terms, is the change in heat of a reaction. The delta H equation to find is simply the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. Now let's do a quick demonstration to find delta H. First, we have a reaction. Now, in this reaction, you can see that ammonium nitrate is being dissolved into an ammonium ion and a nitrate ion. So here we have the different enthalpies. Here we have the work spelled out for us. Now here, if we were to follow this equation again, we have the sum of the reactants, the sum of the products enthalpy minus the sum of the reactants enthalpy. So here we have negative 132, which was on this little chart that he gave us. Negative 132.51 plus negative 205 minus negative 365.56. And that will leave us with 28.05, a positive enthalpy change, which means that this reaction was an endothermic reaction because the system gained heat instead of losing heat. Now we're going to try to find delta S in this Gibbs free energy equation. So the definition of entropy, which is delta S, is the measure of the amount of energy dispersed among molecules. But people tend to think of entropy as the orderliness of a system. To better show this, I have set up here an example. So here we have a very orderly classroom where all the kids are sitting down in their desk, being quiet, and causing no chaos whatsoever. As chemists, we would say that this has an entropy of negative, which means that there's a lot of order in the system. However, in this scenario, we have kids going crazy and the teacher looking as though she's about to explode from the disorderliness of the classroom. We would say that this situation, as chemists, would have a positive entropy. In a reaction, we can determine the entropy change in two ways. First, we can do the exact same thing we did with the change in enthalpy, which is products minus reactants. So if you want to know, we would just do these kinds of equations, these kinds of calculations again, only instead of using delta H, we would be using delta S for each product and each reaction. Now, you don't have to do this if you don't need to find the exact number that goes with delta S. So instead, we can do the following by deducing what delta S might be depending on what kind of products you have from what kind of reactants you have. So here we have a gas, a water or a liquid, and a solid. So gases are the least orderly of the three states of matter because the amount of energy dispersed among the gas molecules. You could also think of it like this. The molecules in a gas are moving around the most compared to a liquid and a solid, making the gas the most disorderly of the three. Then we have a liquid, which is not as orderly as a solid, but more orderly than a gas. Finally, we have a solid, which is the most orderly of them all. So, how do we guess the entropy of a reaction? Simple. Say we have a reaction in which a gas turns into a liquid. So we're going from the most disorderly of the three states of matter to a semi-disorderly, not as disorderly as this one. So we can say that we're just going from a very disorderly system to a more orderly system, which makes this entropy change negative because you're going from more disorder to more order. Now, if we were to flip the reaction and have a liquid going into a gas, this would have a positive entropy change because you're going from a more orderly system to a less orderly system. The same thing were to go from a liquid to a solid. We're going from a less orderly system compared to a solid to a more orderly system, or the most orderly system. So this entropy would be negative because you're going from less orderly to more orderly. But if we were to change it around, we would be going from more orderly to less orderly. Now, regarding the reactions that have gases as products and reactants, the positive entropy reactions will be the one that produces the more moles of gas than they started out with. So that basically means that if you were to have 1 mole of gas and then end up with 2 moles of gas, this would be a positive entropy because you're going from a lot of disorderly to even more disorderly here. But if we were to flip this around and say that we have 2 moles of gas here and we only end up with 1 mole of gas here, we'd be saying that the more disorderly would be going to a disorderly state, but not as much disorderly as 2 moles of gas. Now, how does this all work back with this equation to figure out how spontaneous a reaction is? Well, in this Gibbs free energy equation, we need to know what the delta H is and what the delta S is if we were to do this kind of calculation together. So we have a simple chart here to discern between the different signs for delta S and delta H. So this basically means that in this equation, if delta S is negative, that would mean that delta H would have to be more negative than delta S multiplied with the temperature, in order for the Gibbs free energy to be negative, making the reaction spontaneous. However, if delta H is negative and delta S is positive, meaning that this is a more disorderly reaction, then Gibbs free energy is going to be spontaneous because it's going to be negative at all times. If we were to have a very positive delta H and a positive delta S, then we would have to have a very high temperature in order for Gibbs free energy to equal a negative number, because you're multiplying T times delta S and subtracting it, meaning you want a very large number on this side so that this whole thing turns out to be negative. And once you just memorize this equation and play around with it for a little, you seem to find patterns, and after you find patterns, it's very easy to deduce whether or not your reaction is going to be spontaneous or not.